let us now continue with this electromechanical energy conversion. Last class we discussed the whole gamut of devices which use the principle of energy conversion, which convert energy from one form to other, electrical to mechanical and vice versa. And then we took up a simple case of a singly excited magnetic field system, which is represented here. And we came up with the expression for the energy stored in a magnetic field like this, which is basically to what extent you can magnetize the circuit. So at any given time, certain magnetic field energy is stored, and any changes in the magnetic field energy is the one which is resulting into an electrical system in the form of response voltage to the mechanical system in the form of response force. Okay. So this electrical circuit, the field response in terms of voltage current, mechanical circuit field response in terms of force displacement and so on. Now the expressions we derived were that that the stored energy is equal to, whenever that system which is expressed, so 0 to lambda I d lambda, and we also said that accordingly the force of electrical origin in a singly excited system is obtained as a space derivative of the stored energy, that we call it as minus delta W field by delta x. Okay, that is the rate of decrease of the stored energy with reference to displacement x. Okay, and we also know that from this we got another expression, that is I as what did we got I as? Delta W field by delta lambda. Okay. Now that means this stored energy, you take a derivative with reference to mechanical variable x, you get the force response, and this stored energy you take a partial derivative of the flux linkage electrical variable and you get the response current. Now this stored energy is a function is represented in terms of lambda and x, isn't it? This is important, that in which function you represent is important. It should be in terms of lambda and x in all this. Okay, only then you can take the partial derivative of this. Now by definition, what do you mean by a partial derivative? You mean a partial derivative means while taking the derivation you keep the other variable constant. That means when you are evaluating the force is the negative change of stored energy with displacements at constant lambda. Is it clear? And similarly the current response is the derivative of the rate of change of the stored energy with the flux linkage when the displacement is constant, when the x is constant. Okay, so this is what we have learned in the last class. Now we have also seen that there is a variation of lambda with current, which typically goes like this for a given x. If you hold the x constant in a system like this, it varies in this fashion. Non-linearity is due to the magnetic iron part of the magnetic circuit, but if it is only air portion, it would be totally linear. Okay, and we say that if you have for any given value of let us say I naught, you have a specific value of let us say lambda naught. Okay, that means you have excited the coil up to I naught from 0 and you reach lambda naught. Okay, now we also learned in the last class that I will let us say you call this as some A, let us say this point B. We said that area OABO is what? It represents the energy stored. Okay, this area you represent as the stored energy. Because that is any I d lambda, if this is d lambda, so that is nothing but you integrate from 0 to lambda naught I d lambda, isn't it? So if this is d lambda, you take I d lambda from 0 to lambda naught. Is it clear? Now let us look at there is another area that is, let us say OA, I call this as C. OACO. Is it okay? You are seeing another area. I mean, I'll hatch it like this. Okay, and this area is equal to what? So it is basically the lambda naught I naught minus W field. Is it clear? For a given situation. That is the total OACO minus OABO, isn't it? Okay, this is the area. Now we define this area. Is it okay or not? OBAC, sorry. This is OBACO minus OABO. Okay, now this we call this area as this is defined just for our convenience as co-energy. It's just mostly a mathematical expression, and it is generally indicated as W field prime. W field dash is called a co-energy. Okay. I told you it has limited physical significance. Mathematically it is defined like this. Okay, that is I lambda minus W field. Okay. Now with this arrangement, we can have how do you define this W field? We can define it as W field dash can be defined as what? 0 to, how do you define that? Just like we define W field as 0 to lambda naught ideal. 0 to I naught. That's right. So you can have this as 0 to I naught lambda di. Is it okay? So this is a definition that is possible. Now that means here you are considering lambda, you are integrating this way. That means you are taking this as a sort of a variable which depend upon lambda, I as a function of lambda. See, if you are defining this way, you take lambda as a function of I. Here you have to write this as which one? I as a function of lambda. Okay? And with this definition, that depends upon now is represented in terms of this is expressed in terms of what quantities? In terms of what? You see, each of them depends upon electrical state and mechanical state. What is the electrical state? This will depend upon? X. No, it's not electrical state. Okay, electrical state is I and the mechanical state is X. This is an electrical state, this is the mechanical state. Right? So energy is depend both on the electrical condition or electrical state and the mechanical state. Okay, so you express in the I and X. Now if you express this in terms, this W field dash is expressed in terms of I and X, whereas W field is expressed in terms of lambda and X. Okay. Now therefore you can say that dW field dash, if it is expression of these two quantities, how do you write it as? You can write it as this partial derivative delta W field dash by delta X into dx plus delta W field dash by delta I into di. Is it clear? I mean, it's just a simple thing. So you take its derivative, any increment in a given time dt, any change in, you are trying to say any change in the co-energy will be equal to the partial derivative with reference to x into dx and partial derivative with reference to I into di. Okay. Then we also knew that W field original, what was the original equation? We had dW field was equal to dW electrical minus F dx, isn't it? That was what was dW electrical? I d lambda. Anyway, some mishap we can't help now. So we have dW field is equal to I d lambda minus F dx. This is what we know. Our energy balance. Energy balance is increase in stored energy is the electrical energy input minus the mechanical energy output. And okay. Now, what is the dW field? Now, we have, let us go back to our definition that the dW field will be is equal to, for any I and lambda, is I lambda minus the W field we have seen dash is equal to I lambda minus W field, right? Okay. Now, what will be its, with this definition, what will be dW field dash? Will be equal to I d lambda minus lambda plus d lambda I, lambda di minus dW field dash, sorry, dW field. Okay. Now, we can write this as I d lambda plus lambda di minus dW field is here. Okay. So, that is I d lambda from this one, I d lambda plus Fe into dx, right. So, you can simplify this as I d lambda goes, that is lambda di plus Fe into dx. So, that is your value of dW field dash. Okay. So, the what do you conclude from here? How do you get, we have this expression dW field dash is this, and we have another expression. Okay, we have two blocks of equations. See this equation and this equation. So, on comparison, what do you get? So, let us say this equation is equation 1 and let us say this equation is equation 2, right. So, we will end up with these equations. I will rub off others just to remove. Okay, I just left only two equations on the board, this equation 1 and this equation 2. Okay. So, on comparison, so we can say compare 1 and 2. So, what do you get? Lambda is, okay, lambda is delta W field dash by delta I, where W field dash is expressed in terms of I and x. Okay. So, whatever is the singly excited system we are talking about in this field, we are now trying to say we also define another quantity W field dash to get this. Now, the second one is, okay, then we can also find the other expression of force is now equal to what? Sine plus. So, it is most important, plus delta W field dash by delta x, where again it is expressed in terms of I and x. So, this is most important. So, you now have two expressions for force, one in terms of W field, another in terms of W field dash. So, in what variable it is expressed, you choose a proper sign. So, this is important here. So, this sign is important. So, what does it mention? What does it say physically? This expression, what does it say physically? The force is what? It is the rate of increase of co-energy. See, earlier we said the force is equal to minus delta W field by delta X, where it is in terms of lambda and X. So can you tell me these two have to be exactly same? It must give the same force. Two expressions should not give a different expression for force. Now they must be exactly same. So what do you define as this and this? This, yes.
Rate of increase of core energy.
Data?
Rate of increase of core energy.
Rate of increase of core energy.
Huh?
You complete that.
Rate of decrease of field energy.
No, it's the complete statement I want.
Constant I rate of change of increase of W core energy with respect to X.
Yes.
And is equal to the decrease in rate of change of field energy with constant lambda. With changing X.
Yeah. I mean that means to be to make his fuzzy statement little clearer, the force is the rate of increase of co-energy with the displacement at constant current, and which is also same as rate of decrease of stored energy at constant flux linkage, with where rate of decrease with reference to the displacement, both of them. Is it clear? Now that means force acts in a direction to increase co-energy at constant current and acts in such a direction to decrease stored energy at constant flux linkage. Okay? So this is important. Now let us try to understand a little more clearer and see whether what we are talking makes sense. This is, let us say this is at a value of x. Now if you increase x to x plus delta x, where will my curve be? It will go up or down? It will go up. So let us say there is another curve at x plus delta x. I increase this by an increment delta x. Is it clear? So what I have done here is, in this one, I have just increased x to a value x plus delta x. So you come to a new magnetization characteristics, okay, as we have done here. Okay, this will go nearer, and then you have this. Now but the force is acting in the same direction, okay, and that force is counterbalanced by any external force that you can hold on like this, hold the other way. Only then it will be in equilibrium at x. Otherwise, it will move dynamically. Now, if you see this condition, let us say it was at a certain value I naught, let us say, and then where the this was first this at x, what was the, let us say stated W field was equal to area. What area was it? O B A O. Okay, this is at x. Now W field dash was O A C O. Okay, this area, these two areas. Now at x plus delta x, this is at x, this is at x plus delta x. W field is, let us get now we are interested in an operation. Let us say W field, we have said we are trying to operate at constant lambda. Okay, so if you are maintaining lambda constant, let us say this is some A dash or something like that. So your new W field will say O B A dash O, okay, right, at constant lambda. I am making it at constant lambda. We are defining that lambda is constant. Lambda is constant, and we are taking this is new W field. Now what will be the W field dash at constant I? So at constant I means I just, what will be the, let us say, okay, let's say A double dash, right? Now if this is A double dash, what will be the new co-energy at constant I will be O A double dash C O, that is I equal to constant. You are maintaining current constant and going up that way, right? So let us say, that means we are having sort of this triangle, which is, this is what is this A dash, you can call it as what? What is A dash represents? So it is delta I. A dash, you can say the change in current. If you want to, that means there is, you can decrease the current if you want to maintain the same lambda. Okay, so this is a decrease in current that you will have. What is this represents? A double dash is delta lambda for constant I when X changes. Okay, right. Now what we are now trying to say is, what is, according to our conclusions, we would expect that what is the delta W field due to delta X. What is delta W field now? Because we have seen these two are the area, that means this area minus this area, right? What is that area? Please tell me, what is that area? Huh? O A dash O. Okay. O A dash O. Is it okay? Now what is, this is at constant. Now what is delta W field dash? That is these two area difference. W field dash minus this one. Huh? O A double dash O. Okay, A dash comes on the way. Right. Now we were saying that these two areas, so you will see in one case it is an increase in co-energy. This is an increase. So this increase at constant I. This decrease. See, this stored energy is a decrease, where co-energy is an increase as X changes. Okay? Right? As X changes, one you find this was the value and it has increased. Other one, this was the value and it has decreased. Now the two areas must be ideally same. Okay? Are they same? So let us say this is A1, let us say A2. So you say A1 must be equal to A2, this is ideally. That as per our definition they must be same, because force has to be same.
So shouldn't the rate be same?
Pardon? No. This is a differential. That is what we have. This differential must be same, because the force by definition is minus delta W field dashed by delta X, and is also equal to plus delta W field divided by delta X. So these must be same. These cannot be different. But the areas they are not same. Are they same? Are they? What is the difference in the area? So the difference in these two areas, the difference in area, see, because both forces must be same, but there is a difference area which is equal to A dash, A double dash, which is equal to, what is the area equal to? Half of, it's almost, you can say it's a triangle, half of delta I into delta lambda. Okay, this is what it is, half of delta I into delta lambda. Okay, so this, how do you account for this?
That is partial derivative, but so how can you say
What?
the condition be same? The force is delta W, del W field dash by
No, these two areas, we have physically, we have explained everything. We have gone into those areas. We say that these two areas, see, one time we got this area, another time we got this area. We say, but somehow we have landed up with some type of a kink here. Okay, now we should be able to also explain it mathematically and physically.
Sir, but what you are saying is the force is delta W, del W field dash by del X, or minus del W.
No, but that is for any point. We have now taken it, we have increased by a small increment.
Yes, sir, for that delta X to tend towards 0.
So they, you see, already we have got, now, but this area tends to 0. It is again a product of a very, very small quantities, isn't it? So that means as delta, if all our derivatives means as delta x tends to 0, so obviously delta I, delta, they also tend to 0. So this area, therefore area of A dash, A double dash also tends to 0. So we are no problem, we have done no mistake, everything is in order, that both our mathematical definitions and derivations conform to our physical explanations like this. Okay, and this is true whatever may be the linear or non-linear variation of I and lambda. Okay, so this is valid. Any questions? Oh. Okay, now let us take our argument a little further and say what happens if this variation is linear. Okay, now we have took some non-linear variation. Now if let us say magnetic circuit is linear. No saturation. That means assume, so this is what we assume, that magnetic circuit is linear, which means that your I lambda variation is straight like this. Okay, there is no non-linearity. So then what do you get? You know, for any given condition, for any state, say I naught lambda naught, what do you get as W field dash? So this is W field and this is W field dash, isn't it? So what is it? Do you have any?
Depending on the slope, will be same. If the slope is A,
Yeah.
the half A, W field dash will be half. It will only equal. Depending on the slope.
Is it?
Depending on the slope.
Is it true? Huh? Huh? Now, will they be equal or not equal? Huh? How many say yes, they are equal? There will be equal, not equal. They are not equal, even though they are linear. They are only what coming down. I say 1, 2, 3. Huh? You see there are some absentees. Okay. Huh? They are not?
The absentees are saying not equal.
Absentees are not equal. Okay. Now, this is a basics of geometry, that any rectangle diagonal divides the area. I think you went through these Fitzy Brilliants and courses too much, I think. Huh? And you are coming to a situation where you just don't know the fundamental, that any poor diagonal will equally divide any rectangle without partiality on either side. Okay? Right. So therefore, at least okay. Now, if it is I lambda, which is equal to half of lambda naught I naught, and which is, supposing it is in terms of flux phi naught and f naught, which is also equal to half of lambda naught is n into phi naught, and I naught is mmf divided by n. So this is equal to half of phi naught into f naught. Okay, and you define various quantities like inductance. You define inductance is the one which is a flux lambda by I, and you define a reluctance as f over phi, and you define a permeant is phi over f, and you can define some 1 over inductance as I over lambda. Okay, I mean I'll say tau or reciprocal inductance. Yes.
The other class student is asking, sir, what are W field and W dash field? Please define those terms to the other class. So they are asking this question.
No, W field and W field dash. Definition is W field is 0 to integral 0 to lambda I d lambda, and W field dash is 0 to I lambda di. Okay, that is the mathematical definition of this. Now we have seen this is this area, this is the other area. Okay, and these two areas is proven to be equal. Now we know that these are the parameters in which these are defined. You can define in a linear system only inductance can be defined. Please, I want this matter at this point to be extremely clear to each one of you. We define an inductance as a flux linkage per unit current, and that decides upon the linearity. If it is not linear, inductance is not constant. Okay, so please don't assume inductance is constant for non-linear magnetic circuit. Similarly, reluctance is mmf per flux, unit flux. Again, the mmf per unit flux depends again on linearity. You know L over mu. Again, mu depends upon the B by H and so on. Similarly, permeance also will have non-linearity, and reciprocal of inductance will also have this one. So, and each one is equal to this. So, you can represent W field or W field, depends upon which quantity you would like to represent. Okay. Now, we have said when it is W field, you represent in terms of lambda, W field dash in terms of I. So, now we know that the energy is equal to half Li square. Would you want to call it as W field or W field dash? Because though magnitude wise they are same, but we must, for our force calculation, you must define it appropriately. So it is defined as co-energy. Okay, and you can also call it as W field if you write in terms of half lambda square into tau, right? Is it right? Because I define as 1 by L. This is 1 by L.
So what is this called?
This is reciprocal of inductance. Okay. So this is how. What is it? Lambda square into tau. Say, is it okay? 1 by L. Now similarly, we can also, this is what W field or W field dash? This is W field. Okay, similarly you can have W field as half of phi square into reluctance, isn't it? Because half of F into phi. Half F into phi, because F is equal to phi into reluctance. So half of phi square into reluctance. So that is W field. And similarly you can have another quantity W field dash is half of F square into permeance. So you can write them in all four possible ways. But you must be sure in what electrical parameter they are represented. Either you call it as W field or W field dash.
W field dash or W field, sir? Half Li square.
There is W field dash because it is in terms of I stored. Magnitude rate is same as W field. See, these two magnitudes are same, but for our convenience we do like this. So we could summarize this like this. Okay, we represent electrical variable in terms of current and inductance. There are two things, electrical variable and X dependent term. So inductance will be therefore be depend upon X, isn't it? Inductance depends upon the value of X. Now that, and here you don't call it as W field, but as we said we call it as W field dash because it terms of I. So it is half Li square. Now what will be the force equal to? I square into its partial derivative, you keep I constant. So I square dl by dx. Don't try to differentiate I also with x, please. So all of you please note down, you write it in this thing, don't differentiate this expression with reference to I, its partial derivative. Okay, at any point in your tutorials. I square dl by dx. Half, sorry. So it will be half I square dl by dx. Okay, next, let's take the next one, that is MMF, it in terms of MMF F and permeance P. Then again it is not W field, it should be W field dash because you are representing in terms of MMF F. Okay, so it will be half of P F square as we have seen there, half of F square P. So what will be the force now? Please tell me what it is. Half F square into dP by dx. Now you are taking the derivative of permeance with x in a given. So you get the expression for force in a singly excited system. Okay, then you have a flux linkage lambda, right? Is the electrical variable is flux linkage lambda, and you have a reciprocal of inductance as tau and half of tau lambda square, isn't it? So that will be not W field dash, it will be W field because you are representing in terms of lambda. Is it okay? Therefore, what is your force expression? Force expression is minus half lambda square into d by dx of that reciprocal inductance, tau. Okay? So you please note that here you take minus. If you take plus, you get a wrong answer. Okay? You must take minus so long as it is in terms of lambda. Now lastly, supposing you represent in terms of flux phi, and then the x dependent term is reluctance R here, and the expression for energy is, now it is going to be the stored energy W field, not W field dash. So because you are expressing in terms of phi, that is half of reluctance into phi square. So what will be the force expression? So it is force expression for this will be this, that is half of phi square into d by dx of that reluctance. Okay, so that means your force acts, to sum up the last column here, if you see, the force acts in a direction to increase the inductance, decrease the permeance, increase the reciprocal inductance, sorry, decrease the reciprocal inductance and increase the reluctance. Sorry, decrease the reluctance. So, decrease the reciprocal inductance and increase inductance. So, force always acts in a direction increase inductance, increase permeance, decrease reluctance, decrease reciprocal of this thing. So, these are our the basic and fundamental thing of the energy conversion principle. Okay. Now, we had one single excited. Supposing you have one more winding like this. Can we extend the same logic? Doubly excited system. So, what we have done is, I have put one more winding on the moving member. Okay. There is one winding, let us say winding 1 and winding 2, N1 turns lambda 1, I1, E1, N2, lambda 2, I2, E2. Okay. Then, assume it's again a linear system. Okay. If you assume it's a linear system, what do you get? You get it as, you can define lambda 1, lambda 2 in a matrix form as L11, L12, L21, L22 into I1, I2. And you define, what is L11? Lambda 1 by I1 when I2 is 0, which means it is the self-inductance of winding 1. Okay, self-inductance winding 1, you call it as L11. Then L12 is mutual inductance between these two. Okay, and mutual inductance between these two is the flux linking winding 2 due to current in winding 1. Okay, flux linking winding 2 due to current in winding 1 when the second is not unexcited, that is L12. Similarly, L21 is flux linking winding 1 due to current in winding 2 when the first winding is unexcited, and L22 is the self inductance of second winding, that is flux linking winding 2 due to current in winding 2 when winding 1 is unexcited. So, these are definition of self and mutual. So, you get these two quantities. Okay. Now, when you have these two quantities, you can what will be dW field now? And all of these are depend on x. Say all these parameters would depend upon x. So, what will be dW field? Okay, tell me which you have not understood. Is this clear? Huh? This inductance, self and mutual inductance. Yes. By definition. This lambda 1, lambda 2 is L11 I1 plus L12 I2. Okay, see, inductance is equal to flux linkage is equal to inductance into currents. Okay. Now, lambda 1, lambda 2, so we can represent in terms of this matrix. These are the diagonal elements are L11, L12 are the self inductances, and non-diagonal elements are mutual inductance between the respective windings. Okay. Now, supposing they are now operating under certain condition. Okay. Now, you make an increment. Supposing you say that whole WXL system is under a magnetic state where you have taken the current here, say from 0 to some value I1, and current here was 0 to some value I2. That means they are all in equilibrium state, a certain flux. That flux will be cumulative effect of both the windings together, right? So, now there is an energy which is there in the magnetic field, right? All over there is energy, and you take the total energy in the magnetic field. In the whole magnetic there is a total energy. Now, I would say supposing you force certain increments in this dW field. So, dW field will be I1 d lambda 1 plus I2 d lambda 2. Okay, as if it is one winding I d lambda. So, you can always write this as I1 d lambda 1 plus I2 d lambda 2. Is it okay? Now, this is the incremental energy we are giving by increase in the flux. So, what will be this? This will be if lambda 1 is defined as L11 I1 plus L12 I2, and lambda 2 is L21 I1 plus L22 I2. So what will be d lambda 1? Please tell me now. What will be d lambda 1 would be? L11 di1 plus this is all at constant x. We are now trying to increase it, so we are only we are not changing x at all. So similarly, d lambda 2 is L22 di1 plus L22 di2. Sorry, L21 di1 plus L22 di2. Pardon? Huh. It's all, see, when you say L11, they are all linear only. Okay, non-linearity is not there. Now, please tell me what is GW field in terms of this. Can you just substitute and tell me what is GW field? So it will be L11 into I1 di1 plus L12 into I1 di2 plus I2 di1, and L12 equal to L21. Therefore, we can write this as d of I1 I2. Right, plus L22 into I2 di2. Right. Now, if you integrate from total energy at any given state of I1 and I2, what you do is assume that the whole system is unexcited. Okay, both of them. Now you increase for 0 to I1, so that it reaches a flux lambda 1. Keep it that way. Then you take the second one and 0 to I2, okay, and it reaches lambda 2. And now you come to a steady condition. So if you do this, it's almost a double integration, 0 to I1, 0 to I2. So if you do that, what will be the stored energy when it has reached the total state of I1, I2? Is integral of this, isn't it? Is integral of I1 and I2. So what do you get it as? Half of L11 I1 square plus half of L22 I2 square plus L12 I1 I2. Now you please note that you don't get half here. So this is the stored energy in the case of a doubly excited system. Now what is that? Is it a co-energy or stored energy? It is co-energy. Just for our definition. So what will be the force? Is equal to plus delta W field dash by delta X at constant current. So you are maintaining the current constant. So please tell me what is the force expression here? Half of I1 square dl11 by dx plus half of I2 square dl22 by dx plus I1 I2 dl12 by dx. So I think this is where we will end today, that we have a force expression for doubly excited system as plus like this. So that means you must know how the self and mutual inductances change with x. Don't bother about currents, are all to be kept outside the differential I1 and I2, and we will get a expression for force. So tomorrow we will discuss when you extend to multiply excited system, because most of our systems are several windings are there.
We are adding an extra class.
Yeah, tomorrow, yes, 12 o'clock we had to have it, because we have to catch up with the things. Okay. Yeah, you will be coming here. Okay. So we'll see. Continue in the next class. Okay.